Welcome to this Chemistry World webinar. I'm Natalie Starkey, Chemistry World Science Media Producer, and I'm here for the next hour to fly us to the edge of the solar system and find out more from our scientific experts about the science of the ice giant Uranus. Uranus and Neptune sit alone in what we might call the frozen frontier, being the only major class of planet yet to have a dedicated mission of exploration. So we're looking at why there are space agency plans to launch a mission to visit this icy planet that boasts rings and moons, a complex atmosphere, as well as spinning on its side, giving it the most extreme seasons in the solar system. Throughout this hour, you'll meet two scientists who are excited about a future mission to Uranus, and we'll hear more from them on what we already know about the planet and what we can discover if we make it out there in the future. Following the webinar, you might want to take a look at a recent Chemistry World feature written by Anthony King that actually inspired this session. Mission to Uranus looks at the reasons why we're thinking of revisiting the ice giant Uranus, which of course we'll be discussing here today. So we'll share the link for that in the chat for you to bookmark for later. Now, this session is interactive, which means you can ask questions about any aspect of what's covered, and I'll put your questions to our panel in the live Q&A in the second half of the webinar. You're able to ask questions on the GoToWebinar platform at any time during the hour, even during the presentations. As a quick explainer, on GoToWebinar, there's usually a panel down one side of your screen, although this might be different depending on which platform you're using, especially if you've joined us via a tablet or a phone, or if you're watching on Facebook. Now, somewhere on that panel, there's a questions box, so feel free to pop your questions in there at any time, and I'll be able to put these to our experts later on. Just to let you know, a link of the recording of this webinar will be sent out to everyone who registered, so don't worry if you miss anything, as you can go back and watch again. I will welcome now our guests, who I will invite to turn on their cameras. I'll just give them a few seconds to find the buttons for that. So we have Naomi Rogeli and Athena Kustanis. Welcome to both of you, and thank you for joining us today. Athena is Director of Research with the French Centre for Scientific Research at the Paris Observatory. She specialises in astrophysics and planetology. She contributes to the development of space missions and analyses the acquired data to investigate the atmospheres and surfaces of planets, satellites and exoplanets. Some examples of these have been the NASA ESA Cassini-Huygens mission and the upcoming JUICE and Ariel ESA missions. Now, Naomi is a James Webb Space Telescope Guaranteed Time Observer, postdoctoral research associate at the NASA Goddard Space Flight Center. She's a solar system ambassador for the JWST and obtained her PhD in 2021 from the University of Leicester in the UK. Her thesis used archive data from the Spitzer Space Telescope to study the thermal structure and composition of the middle atmospheres of the ice giants Uranus and Neptune. And we were told today that Naomi actually received a really exciting prize recently. It was announced last night, wasn't it, Naomi? Would you want to tell us a tiny bit about that quickly?
Yeah, it was announced at like 8 p.m. last night. I was the recipient of the DPS NSBP Speaker Award for this year.
That's brilliant. So congratulations. I'm glad that we've got you here today. That's brilliant. So we'll be hearing more from both our speakers in a minute. But if you have any questions already for either of them, then please do start sending those in, and we can, collate those for later. It's nice to have a lot of questions coming in for our speakers. Now, first, I'm going to run a really quick poll. So if we can bring that up on screen, you don't have to participate in this poll, but we just like to kind of hear from our audience to see who you are and what you're working on so that we know who we're speaking to. So basically, you just need to click on the screen if you feel like it to tell us about your experience with the subject of today's webinar. There's various options. I'll give you a few minutes to have a look at which is the most relevant answer for you. You might not be a scientist at all and you're just interested in space, or none of the above. Basically, I think that gives us all the options. Okay, I think that's pretty good if we can close the poll. Thank you very much. There we go. So yeah, we had 71% of you, in fact, are scientists working in a different field. 18% are not scientists and just interested in space. And we have a few specialists in the audience. So that's really good to see. So thank you all for joining us. Right, now we're going to start with Naomi first of all. So Naomi, if you'd like to turn on your camera and find the right buttons to share your screen so that we can bring your presentation up. Brilliant, I can see that now. So I'm going to turn off my camera for a minute and I'll hand over to you.
Great. Okay, so today I'm going to be talking to you about seeing Uranus from space. Let's get all those Uranus jokes out of the way first. So what that means is that I'm going to be talking to you about using space telescopes specifically to look at Uranus. So the space telescopes that we use that are closer to Earth and not the ones that are going there, hopefully in the future. So Natalie already said a little bit about me, so I'll say a little bit more about how I got to where I am. So I did a 4-year integrated master's in physics with astrophysics at the University of Leicester. I graduated in 2012 and then took a break for 5 years, ended up as a physics teacher. And then I ended up back in Leicester for my PhD that I finished in September 2021. And my thesis was looking at the chemical and temperature structure of the atmospheres of the ice giants, Uranus and Neptune, with mid-infrared spectroscopy. And I moved out here to near Washington, DC, where I am now, in October of 2021. And I've been at NASA Goddard Space Flight Center ever since then. And my job here is to support JWST Solar System Science in the Guaranteed Time Observation Program, which is a program run by Heidi Camel. So I'm going to start with a poll as well. So another one. So I'm going to mention a load of different telescopes in this, and I wanted to kind of check which ones that you've heard of. So if you guys want to go ahead and pick as many as you want, and any options that you have heard of in the past, and leave any blank that you've not heard of before or know very little about.
Thanks, Naomi. We're getting some answers in. This is a really good question, isn't it? Because you might want to just expand on the top one. What does VLT stand for? I don't think it's giving too much away.
Yeah, so the VLT is actually called the Very Large Telescope. And that's in Chile, in Paranal, Chile, and Hubble. Then there's the Hubble Space Telescope. Then the next one is the Keck Telescope. That's in Hawaii. That's another ground-based telescope. Then Spitzer Space Telescope, and also the JWST. So.
Okay, if we can reveal the answers, actually really interesting.
Yeah.
So we've got no surprises. 95% of people have heard of Hubble, which is no surprise because it has been around for a while, hasn't it? But yeah, so, and then 62% for JWST. That's a very recent telescope, isn't it? So that's good. But yeah, the others not quite so well known, but probably doesn't surprise us, does it?
Yeah, I'm actually impressed at how many people know about Spitzer. I thought that was going to be the one that was the least known, but I'm excited to see that it's not, and that people have seen VLT, but Keck is our least known. Okay, that's interesting. Right, so let's start with the one that you all knew the best. So it's the world's most famous space telescope still. Hopefully JWST one day will take over. I'm quite impressed considering JWST has only been in that air about in space for about a year, just over a year, that it's the second most exciting one. So Hubble launched in 1990, so it's been around a while. It was launched into a low Earth orbit where it's still going strong now, and it's actually almost exactly the same age as me. And in that time, it's done over 1.5 million observations and produced beautiful images and done groundbreaking solar system science. So it's been looking at all the outer planets for decades now. And here you can see some example Hubble images of Uranus, and it's tracked multiple seasons at the planet. And Uranus rotates on its side, which is unlike any other planet in the solar system. So this left image, these left images here show how strange that change in season looks for a planet that's on its side, and that's in just 4 years, considering that the planet has an 84-year trip around the sun. So these two middle images were taken 20 years apart and at different wavelengths, but you can really see the detail with which Hubble can see this very, very distant planet. And now we've only just started with JWST, but you all seem to know a lot about it, which is exciting. And I don't even have any pictures of Uranus to show you yet, but they'll be coming very soon. So watch out for that. And JWST has a 6.5 meter primary mirror made of 18 separate movable segments. It's tennis court size, 5-layer sun shield to protect it from any heat from the sun. And the animation here shows the huge size of both of these observations. And a person there is for scale, seeing the amazing scale that we have here. And it was launched, the JWST, Christmas 2021, so not long ago. And then it had 6 months of travel, deployment, and commissioning. So it traveled to its home at the L2 Lagrangian point, 1.5 million kilometers away. And it deployed by unfolding on its way, and commissioning was getting the telescope ready for science. So it's only really been doing science observations for less than a year. And it's the premier observatory of the next decade. It's going to serve thousands of astronomers worldwide. It already has done so many observations already, including in the solar system. And building it already was an international collaboration between NASA here in the US, the European Space Agency, including the UK, and the Canadian Space Agency. So Spitzer Space Telescope, a lot of you haven't heard of Spitzer Space Telescope, which is sad, but also exciting that I get to tell you about it. Spitzer was launched in the same generation of telescopes as Hubble. It was launched in 2003, and it was decommissioned actually only very recently in January 2020. It was in an Earth trailing orbit, so following us around the sun, and it's pretty small compared to these other two telescopes. Its mirror is less than a meter across. And if we now compare directly these three telescopes, one of the big differences is their mirror size, but also their wavelength range. So for telescopes, bigger always means better. So larger mirror means more collecting area. We can look at dimmer, smaller, colder, more distant objects. And JWST's mirror is an area more than 5 times greater than Hubble's and 45 times greater than Spitzer's. And one of my favorite facts is that the Spitzer mirror is the same size as the mirror, the secondary mirror on the JWST. So that's the mirror that is on the end of those booms that reflects the light back into the instruments. So that's the same size as the Spitzer mirror. And another big difference is their wavelength range. Hubble works in shorter wavelengths, mostly in the visible, but it works from the UV through the visible into the near infrared. And JWST and Spitzer work exclusively in infrared wavelengths. So they're looking at heat instead of the light that we see with our eyes. And that's useful for planetary science because we can look through the clouds and hazes and see the thermal and chemical structure of atmospheres. And my PhD research used the Spitzer mid-infrared spectrograph, or the IRS, or the infrared spectrograph. So if bigger means better for telescopes, then why not just use these huge telescopes that we have readily accessible on the ground? Why even bother going to space in the first place? Well, these facilities on the ground are more accessible, so we do use them a lot, but we have problems with the atmosphere. So this grey image here of Uranus is in the near infrared from the Keck telescope. That is a 10-meter diameter mirror telescope based in Hawaii. And the blurrier orange image, that's in the mid-infrared from the VLT, or the Very Large Telescope, that's based in Paranal, Chile. That's an 8.2 meter diameter telescope, so both huge telescopes. And we do get these incredibly good images, but not as good as the images that we can get from space, because we only get them at very specific wavelength bands where we have windows in the these optical windows in the atmosphere, because the Earth's atmosphere absorbs all the interesting things that we want to look at. It really gets in the way and absorbs that signal, especially at mid-infrared wavelengths. So why is mid-infrared useful in particular for these planets? So here's some example images of Uranus from visible through to microwave. And these different wavelengths are sensitive to different depths in the atmosphere. So on the right, this shows a vertical structure of Uranus's atmosphere. And we're showing the stratosphere and the troposphere separated by the tropopause. So everything above the tropopause is the stratosphere and everything below it is the troposphere. And we see where each of these wavelength bands sense. So visible in the purple senses the cloud tops, and we see in the image the typical blue color of the planet that's caused by these high levels of methane in the atmosphere. And then in near infrared, so in the blue, it senses the cloud tops, but then also these tropospheric hazes we can see a little bit more. Then in the microwave, it sounds deeper, so that's in the green, it sounds deeper into the troposphere. But then in the mid-infrared, we can see both the stratosphere and the upper troposphere. So these depths are what we call the middle atmosphere, and these images here are two of Uranus in different bands in the mid-infrared from the VLT. And we see different structure of the troposphere compared to the stratosphere, all in mid-infrared. And the stratosphere is extremely exciting to be able to look at because it contains the complex hydrocarbon hazes that dominate stratospheric processes. So when methane is elevated into the stratosphere by convection and storms, etc., it's broken down by the sun. It's broken down by photolysis or photodissociation from the sun. And when that happens, it then reforms into complex hydrocarbon chains like acetylene and ethane and others. And observing these chemicals tells us a lot about the chemistry, about the temperature, about the dynamics of the atmosphere. So I mentioned about Spitzer. Spitzer was used to observe Uranus in 2007 because the telescope's so small and Uranus is so far away. We have a small problem. We can't get any pictures. So we have to treat the planet like we would a star, a point source. So we only get spectra like this example here. So from one dot of light, we spread it apart and we get lines like this. So the top and the bottom panel here show exactly the same thing, just in different units. And so the bumps and the troughs in the lines show us what the atmosphere is made of, what temperature it is, and also with modeling, it can tell us how it changes at different depths. And we can see the main features: methane at 8 microns, and those complex hydrocarbons we were talking about, like acetylene at 13 microns and ethane at 12. And the overall shape of the spectrum is governed by temperature and also the collisions between hydrogen and helium and hydrogen-hydrogen. And I'm going to show you an example of how we use this data to investigate the temperature and the chemistry of the planet. And these spectra are global averages made up of multiple longitude measurements averaged together. So as Uranus spins, like in the animation here, we're looking at an average of all of those different faces of the planet. So for my PhD, we split apart these different faces to look to see if anything is changing between them, and we call this longitudinal variability. And that's not as easy as it sounds for Uranus because it's tilted on its side and has these very extreme seasons because of it. The animation here shows what Uranus looks like during a Uranian year, so that 84-year Earth year period as it travels around the sun. So that's what it looks like from Earth. So when Voyager looked at Uranus, its south pole was facing directly at us and facing the sun, and we couldn't view the northern hemisphere at all during that time. And we can only do this kind of longitude study during and around the equinox, when we can actually view both northern and southern hemispheres together. And that's every 42 years at this equinox period. And the last equinox was in 2007 when the Spitzer data was taken. So do we see a difference between the longitudes when we split them apart? The answer is yes, we do. We see a consistent variation, which isn't what we were expecting because it's the opposite of what we saw at Neptune. So the right plots here show the difference in radiances for the entire wavelength range of data. So the important thing to notice is that the longitude 3 that's in green is consistently dimmer than longitude 4, which is in purple, which is consistently brighter. And that's not what we were expecting. So to look closer, we look at each chemical species in the spectrum. So this is shown by the bands in different places shown in the plot. And each species here contributes to a different height in the atmosphere. So this plot shows the contribution for each pressure level. for each wavelength. And as an example, we have methane here. Methane contributes to higher up in the stratosphere, whereas these two in green and yellow, they are hydrogen, helium, and CH3D, which is a different type of methane. They contribute to deeper down in the troposphere, so below that tropopause level. So what we can do with this information is we can plot the variation of each species as Uranus rotates. So we see that the green and the yellow species that are in the troposphere, they don't vary between different longitudes at 360-degree spin. Nothing changes. Whereas the methane, the stratospheric component, that does vary a lot, up to 15%. And we see that same variation in all of the stratospheric hydrocarbons at varying levels. So we know we have a longitudinal variation in the stratosphere, but we don't know whether it's a variation in temperature or gas abundance or what physical process or feature is causing it. So there are different ways to find clues. One way to find a clue is to get some spatial resolution to see what's going on. And we looked at ground-based telescope images like this one from the Keck telescope, and we saw some clues that it could be linked to storm activity. But we can also use modeling. And we use a software called Nemesis to do something called optimal estimation retrievals of the data, something that they also do using remote sensing at Earth as well. This left plot here shows that data compared to the model. And then what we do is we model each longitude separately, and we try to find which parameters need to change to cause the changes that we see in the spectrum. And we found it's realistic that it could be a change in temperature only. And so this right plot here shows the changes in temperature needed for the variation that we see. So we only need around 3 degrees temperature difference in the stratosphere to cause the changes that we see in the spectrum, which is a very realistic change in temperature for an ice giant. But these are just guesses as to what is going on the planet, and we are patiently waiting to see if JWST can give us any more clues. So how is JWST better? We are currently frequently we have to choose between information or images. So we have to choose between finding out what something's made of and what it looks like. So either information like Spitzer can give us with its spectra, or images from large ground-based telescopes that are only in certain wavelengths. Whereas JWST can give us both. It uses something called an IFU, or an integrated field unit. Basically, that means that every pixel in a picture that it takes has a spectrum that we can look at, like the ones that Spitzer give us. And this forms something called an image cube because it has 3 dimensions of information. And here's an example of a model of what the MIRI IFU is going to see. So the mid-infrared IFU on JWST is going to see when it looks at Uranus. And each pixel in this image is going to have an associated spectrum like the snippet shown above. And this spectrum is even better than the Spitzer spectrum. And we have hundreds of them, 1 for each pixel. And we can use this to look at the spectrum or the specific feature like a storm, so pick out the pixel that has the storm in it and see if this is the cause of the global changes that we see with Spitzer. And I can't show you any real JWST Uranus data yet because it was only taken in January. But what I can tell you is that it looks remarkably like the model. So I'm PI of some Hubble time that's looking at both the ice giants to help JWST. So we're using Hubble and JWST together to get even better science. And we've used the WFC3 UVIS instrument to collect visible and near-infrared images of Uranus in January at the same time as JWST. And JWST can't look invisible, so it expands our ability to see certain things, especially these dark spots. Dark spots are very unique to ice giants, the famous one, the Great Dark Spot at Neptune. We also see them at Uranus, like this example image here from Hubble. And they're associated with storm activity, we think, and they're only visible at blue wavelengths, so we definitely need visible to see them. We need Hubble. And also with those IFU or image cubes, we get a lot of information, but we sacrifice a little bit of spatial detail. So we can get better detail from Hubble in the near infrared to identify finer features like small storms or clouds. And something called the opal or Outer Planet Atmospheres Legacy program has been observing these planets with Hubble since 2014 consistently. So we'll also gain the ability to look at how it changes over time. So we'll gain some temporal context because of that. And there are actually multiple programs that observed Uranus alongside JWST as well as our program. We have additional HST observations in the UV. We have XMM Newton looking in the X-ray, and the Huge Mirror of Keck. They all took images of Uranus in January. So the results from those observations are something to look forward to, along with these other things as well. So there's more Uranus will be coming in the cycle 2 of JWST observations, which start towards the end of this year. And the next speaker, Athena, will be talking more about the exciting future mission that should be heading to Uranus soon. And all of this remote sensing that I've been talking about, we do with the stuff that we do with the space and ground-based telescopes, that helps to prioritize the science that we want to do when we do finally visit, and it's really important for this future mission that hopefully will happen. So yeah, thank you for your time, and I'm looking forward to your questions later.
Brilliant, thank you so much. Wow, I've learned loads there, and I'm amazed at like the resolution of JWST, the information you're going to get. We're really excited to see that, so I'm looking forward to that coming out soon. But yeah, it looks absolutely incredible, and it's amazing to see how much we're doing with space telescopes and ground-based telescopes. You know, we don't always need space missions, but actually they are very handy, and I think that takes us on really well to what Athena's going to speak about. But you know, it's really interesting to see that actually before we launch that huge mission, there's still loads that we're learning along the way. So we have loads of questions coming in, but anyone watching at the moment, even on Facebook, if you have questions, please pop those over to us, and I'll put those to Naomi and Athena at the end. So yeah, thank you very much, Naomi. That was brilliant. Athena, can I welcome you to turn on your camera and share your presentation now? Let's see if we can get that up on screen. Loads more questions coming in. I'm very excited. This is
yes, let me know.
Learning. That's great. Yes, that's up on screen. We can hear you, we can see you. So I'm going to turn my camera off now and hand over to you. Thank you.
Thank you very much, and many thanks to Naomi for a wonderful presentation. She took us out of space already, so my task is going to be to take you a little bit further, all the way out to Uranus. And I do not dispute, absolutely not, that we need the ground-based observations to actually develop the space missions that we put out there. But I'm also going to make an argument for in situ observations, that is, to be out there. I just want to start with a little bit of history here, because Uranus was discovered in March 1781 by the well-known astronomer William Herschel, and more than 200 years later, the NASA spacecraft Voyager 2 flew past Uranus in January 1986, and this was our first ever close encounter with the ice giant planet, sitting at 20 astronomical units, that is 20 times further out from the sun than the Earth, and the only one since then, that is 36 years ago. And it's important to put us in this kind of context. At that time, actually, a few years later, I was a PhD student at Paris Observatory in Meudon, and that's what you see here at the right lower panel image. And I was working for my thesis in astrophysics and space techniques, and I was given a chance at the time to work with some of my NASA Goddard Space Flight Center colleagues on some of the infrared data that we had recovered from the IRIS spectrometer on board of Voyager. And we looked at things like the albedo, the effective temperature and energy balance of Uranus that we published in a paper 1989. And since then, I've been involved, I can say, in several attempts to bring the ice giants back to the forefront of space exploration. And I have been doing that and working with colleagues from Europe, like Lee Fletcher and others, and in particular from the UK, but also people from the US and elsewhere. But I have to admit that until recently, I had largely failed. However, it seems that the momentum of the scientific community is now sufficient to boost the dynamics behind such a mission, in particular for Uranus. So while waiting for this to happen, I had a chance to contribute as part of the scientific community via research that I conduct in planetology, specializing in the outer solar system and exploration of the icy moons also. I've worked a lot with the Cassini-Huygens mission, which is going to be an enormous heritage for all the other missions we send out in the outer solar system, but also by a number of committees that I currently chair or participate, like the ones that you see here on the screen, for ESA, for the Space Agency in France, and for Coast Guard. But let's discuss, I'd like to discuss a little bit further, complementing Naomi's presentation, the why and how we can further explore Uranus. I will pose that we know a lot more about the inner solar system than we do about the outer solar system, and this is for obvious reasons. I mean, everybody understands that it's further away, more difficult to access and to study, with specific constraints on launch windows and trajectories and so on. So for these reasons, the giant planets have eluded in situ regular or even sufficient, I would say, exploration, which is a huge drawback in our study of the formation and evolution of the solar system. So we know today that the internal and outer parts of the solar system are actually connected, even more so than we thought before, thanks to the discovery of the effects of the migration theory. But already in the outer solar system, there are significant differences between giant planets, gas giant planets, or Uranus, the gas giant planets and the ice giants, but also Uranus and Neptune. We understand today that they are different from the gas giants in chemical composition, because we think they were likely formed further out from the sun with heavier elements in place. And we call Uranus, as you heard before, and Neptune the ice giant. And I think this description brings to mind images of a frozen world, but the name mostly distinguishes them from the gas giants, Jupiter and Saturn. I think their true nature is surprisingly obscure. We may discover things that do not correspond with this frozen model in the future. Planets like Jupiter and Saturn have been explored much more recently with probes and orbiters like Cassini, or currently in the Jovian system we have Juno. But the two ice giants that are sized between the rocky worlds and the gas giants, you see here their masses compared to Jupiter and Saturn, are the least known planets in the solar system. So Uranus and Neptune represent a distinct, in my mind, class of planets in the solar system and beyond. Whereas Jupiter and Saturn are made mostly of hydrogen, the bulk compositions of Uranus and Neptune are dominated, as I said, by heavier ices like water, methane, hydrogen sulfide, and ammonia. And they formed slowly, and at their interiors you have at great depth a superionic water ice mantle instead of the metallic hydrogen that we see in Jupiter and Saturn. And so these ice giants may be actually representative of similarly sized planets common throughout the galaxy, but remain, as Naomi was saying before, the least investigated planets in the solar system and the planets that we know the least about today. So Uranus compared to Neptune on the right here, Uranus presents a compelling scientific target, providing a unique opportunity to explore an ice giant system with its 5 classical satellites, potential ocean worlds with drastic surface features, and we have also a dynamically full and apparently haphazard system of rings and small moons around there. And it's also subject to the planetary and magnetospheric effects of its highly tilted. You can see the brooch I have here today, that I had it made a long time ago for Uranus, and it's upside down. So it's really tilted rotational axis, being almost in Uranus orbital plane, and it's a strongly multipolar intrinsic magnetic field. So however, as Naomi mentioned, and as these images demonstrate, Uranus is no longer the bland planet that Voyager revealed. It is a banded world with storms, waves, and extreme contrast. Neptune here to the right is self-luminous. It has an immense internal energy and it powers storms. But in the case of Uranus, Uranus emits no more heat than it receives from the sun. So the question is, has it already been lost, or is it somehow locked somewhere inside? So we have two planets where we have high contrasts in their dynamic atmospheres, extreme seasons for Uranus, and dramatic meteorology on Neptune. And this is another way of showing what Naomi was talking about, images to recall what we know today about Uranus's temperature structure as derived from the Spitzer observations that Naomi discussed, and compared to vertical profiles of methane, ethane, and acetylene, and the approximate locations of the Uranus methane and hydrogen sulfide clouds. And as Naomi said, hydrogen probably comprises, 4/5, so we're talking about a giant planet, of the Uranian upper atmosphere, with the remainder mostly helium, but also important cloud-forming molecules. We have carbon, oxygen, nitrogen, and sulfur in place. I mean, Earth has one main condensable water, which forms clouds, precipitates out, and transports heat, creating weather. But Uranus has at least 4 condensable molecules, water, ammonia, hydrogen sulfide, and methane, to form clouds in the troposphere. And at the uppermost levels, methane condenses into bright patchy clouds that you saw in the previous images. And then it forms the haze that Naomi mentioned. So this is very complicated. It's a complicated place to do spectroscopy and to find out what exactly the composition is. We have all these different cloud levels going deeper and deeper. Eventually, as pressure and temperatures rise at deeper levels, decks of water ice and ammonia ice clouds may form, but it's really hard to say how much water is present below the clouds because we can't study it via remote sensing. So we don't know exactly how and where all these clouds are formed and how what they do in this kind of medium, and how to understand the ice giant atmospheres. Because unfortunately also Voyager 2 had cameras that missed wavelengths beyond orange, and there's a lot of extra cloud structure that you can't see without the infrared wavelengths that Naomi was mentioning. So these, besides the remote observations that Naomi was defending, it is also essential to have something very close by. You need to have a spacecraft that is studying the Uranian atmosphere with spectrometers, with long exposures, so that we can get a monitoring with high spatial resolution. And also we need a probe that can get inside the atmosphere, something like the Galileo probe that entered Jupiter's atmosphere in December 1995. And that probe survived crashing pressures to record water, methane, ammonia, hydrogen sulfide, and traces of hydrocarbons, failing only inside Jupiter around 22 bar. But scientists hope that if we go to Uranus with a probe, we could get down to 10 bar at least, and then possibly 20. And some people, very optimistic like myself, we hope as pressures as high as 50. And though transmitting the signal back to the orbiter could prove challenging at those depths. We don't know much about the internal structure and composition of Uranus and Neptune. Uranus is unlikely to have a layered interior with distinct mantle and core, given what we learned from visits to Saturn and Jupiter. But we have some fleeting glimpses of the Uranian gravitational field and magnetosphere from Voyager 2. But better insights require really a dedicated orbiter, because while the mass and radius of Uranus are known, models only sketch its structure from patchy data. And so we don't know, and until we go there with a dedicated mission, we won't know for sure how this is working. But also another thing is that the moons around Uranus is a very strange ensemble of moons that really deserve further close-in studies. Before Voyager 2 began observing Uranus, there were 5 known moons, named after, as you well know, characters from Shakespeare. You have Miranda, Ariel, Umbriel, Titania, and Oberon, shown here compared to Dione, which is one of Saturn's satellites to scale. But the spacecraft discovered 11 new moons, and 27 of them are now known. And these moons were revealed by the flyby that showed geological activity on some large ice rock moons, and these are potential ocean worlds. Titania and Oberon may be large enough to harbor subsurface oceans, especially if their water layers contain sufficient amounts of ammonia or another antifreeze. A third, Ariel, might have been tidally heated to the point of creating a water ocean in its interior. So this makes them a very makes them very interesting in terms of astrobiology, for instance. Thus, you can see here some pictures quickly as examples. On Ariel's surface, we find smooth, flat floors, perhaps indicative of flows, extension of faults, and other features. And on Oberon, to the right, we have possibly the presence of organic material in what we see here taken with the RTF SPECS spectrometer. And also coming back to the heat fluxes that I mentioned before, the strange tilt and the possibility of a collision may actually be linked to another observation that sets Uranus apart from Neptune and the 2 gas giants, because these planets radiate away the heat generated at the time they condensed and compressed matter during formation. While Neptune, as I said before, emits around 2.5 times more heat delivered by the sun, Uranus is in thermal equilibrium. So Neptune seems to have lots of heat left over from the formation, while Uranus has almost none. So one consequence of this is the more placid atmosphere on Uranus that we have than on turbulent Neptune, as seen in the images. But we don't know why this is the case, and we're still trying to piece together whether the ice giants migrated out and one knocked Uranus over, whether they swapped places. And such early planetary evolution really requires good gravity field data to figure out what is Uranus' internal structure. And so the planet's moons and ring system, they connect, they move around its lopsided axis, as you see here. The rings are not as developed as around Saturn. The Uranian rings are very dusty, and they contain a lot less ice than the rings that we see around Saturn, for instance. But they could be conceivably remnants of a past collision. And an orbiter can study them and bring into light the resemblances or differences in composition between the rings and the moons. So I wanted to give you a little bit of information on a mission to the Uranian system that could come in the years start to be developed actually from now on in the years to come, a dedicated mission to Uranus, because of course the ice giants have been a top priority of the scientific community for a long time. They were advocated by teams in Europe and elsewhere in the world, especially in the US. I was part of the steering group for the Origins, Worlds, and Life, NASEM, that's the National Academy of Sciences, decadal surveying, planetary sciences, and astrobiology for the next decade. And we achieved consensus during that exercise that the next large mission, the next flagship for NASA, should be a Uranus orbiter and probe. So I'll give you a summary of the study here and try to walk you through in more detail in the next slides. But you can see here that this is really for an in-situ and multi-year exploration of all the aspects of the system. This will be a first dedicated study of a place where we could find categories among exoplanets in the future. It's a mission that doesn't require innovation in technology. It's ready to start and go from the heritage it has. It should launch on a very strong rocket. We advocate here for the Falcon Heavy expendable. We have optimal launch windows before 2033, but ways to go beyond that, and a strong international interest, as I said before. So a Uranus mission would enable a large spectrum of multidisciplinary and cross-disciplinary studies that can address priority questions on the formation of the outer solar system, the structure and evolution of giant planets, their moon systems, and even exoplanets, and astrobiology aspects. So we will get insights in processes, origins, habitability, and interconnections. And some of the science goals I started already explaining to you are shown here with the origins, when and where did Uranus form? Did they migrate with Neptune or swap positions? Did a catastrophic giant impact tilt Uranus? How did it happen? What is the internal structure? Then for processes, what mechanisms are transporting heat, energy in the planet? And satellites today, how are the components in the Uranian system, how do they interact with each other? Are there external factors that are altering the system? How does the solar wind interact with the magnetosphere? And also conditions in habitability, as did any of the Uranus moons have oceans in the past, or do they still have today? And so for the origins, for instance, more than half of the Grand Track migration simulations, Grand Track is the hypothesis that proposes that Jupiter formed at a distance of 3.5 astronomical units from the sun and then migrated inward, reversing course due to capturing Saturn in an orbital resonance. But these models that are really very important for us today have completely changed our perception of the formation of the solar system, show that Uranus and Neptune swapped positions, and we should be able to better investigate the when and where the ice giant planets formed by looking at the composition, including for isotopes and noble gases. But the composition will also allow us to constrain the protosolar and accretion models more generally, while at the same time, if you get the in situ composition and gravity measurements, we will be able to answer questions more generally about the formation and evolution of the planet, the role of giant impacts and its obliquity, the internal structure and the internal heat. And processes I mentioned before, many complex and important processes in the Uranian system will have to be investigated, like the one shown here, what led to the current internal structure, how and where is the Uranian dynamo generated, and how the magnetosphere interacts with the rings, the satellites, and so on. And finally, habitability. Habitability is an important aspect in all our exploration of the solar system these days. We look for habitable environments all over the solar system. I put together a poll, if we can bring that up, about habitable conditions.
There we go. So this is a great question. What do we need for life to start? So I've probably made the answers to this poll quite hard because I think we all think we know what the answer is. But actually, let's see what people make of the poll. So we'll give people a couple of moments. Okay, let's close the poll there and just bring up the answers if we can. Yeah, so there you go, Athena. I'll hand back to you. If you can see the answers there. Mo, it was between we don't know yet and the top answer, which was light, energy, water and organic matter. Could you reveal which was the correct answer?
Right, excellent. And I think people are correct because we go for the conditions that at least astrophysicists use to say what are the habitable conditions, that we need water, we need organic matter, and we need energy. I mean, light, I think, also counts for energy in some places, but when we are up there in the solar system, any kind of energy source, whether chemical or, you know, from tides and so on, will count. So these are the conditions, and you have to have that in a stable environment. So we need to look at the moons of around Uranus for possible subsurface liquid oceans via, you know, the evidence of past, for instance, resurfacing, among other techniques. And we will also look for active plumes, because that would be an indication of energy sources or subsurface internal heat currently in place. So a lot of things to do in terms of habitability. I hope this is, yes. And then the interconnections, important how to know the solar wind interacts with a complex tilted magnetosphere, and prioritize actually the ice giants. What is their size the most common among the exoplanets detected in our galaxy today? Among the thousands of exoplanets we have identified today, there is a whole category of exoplanets that correspond to Uranus or Neptune-sized planets. And so we very much look forward with also James Webb to find out, to discover more local ice giants and have some extrapolation from our studies in our solar system to go beyond. And of course, mission synergies. I mentioned before that we will have heritage from missions like Cassini, Galileo, and we have strong international interest within NASA, but also abroad, and the scientific community is ready to go there. You see all these reports over the years. And there is a possible collaboration between ESA and NASA that has been identified early on for a probe mission, something like perhaps Cassini-Huygens, complementing a flagship mission, an orbiter going to Uranus. There are discussions currently between the two agencies on how to push forward with this mission. The design is shown there. I just want to highlight a possible payload with magnetometer, several kinds of cameras, also a spectrometer, absolutely necessary, and comprehensive fields and particles suite, radio science with an ultra-stable oscillator. And the probe would, of course, have to carry atmospheric structure, mass spectrometer, also the ultra-stable oscillator and orthopara hydrogen sensor. Flight time is something like 11 or even 13 years, depending on the trajectory chosen, and we hope to go on a very powerful rocket like Falcon 9 Heavy expendable. And the cruise would take us there in about, if we flew in 2033, would get there about 2044 or 2045. And that would be a wonderful time to study these ice giants. You see in this graph how many times we've gone around some of the other objects in the solar system, but the ice giants out there on the right remain with just a couple of flybys. And really, this is a good time now to return with the Uranus mission, which is technically feasible and cost-effective with thing, and really science compelling. So with that, I'll stop here and give you back the floor.
Oh, wow. Thank you. Goodness me, there was so much information there. And I think one thing I always like to point out to people, particularly if those not involved in space science, is the timescales of these missions. They seem absolutely incredible that you're now working on a mission that may not arrive at its target for, what we're talking, another 20 years or so. And, you know, scientists see their entire careers, don't they? You know, come and go within the lifetimes of these missions, and, you know, things have to be handed over to a whole new set of scientists who are coming onto the scene. Yeah, like Naomi's coming along and she's, you know, going to be following up this work, and it's amazing. But it's a very long way away, and of course this is why we haven't been able to go very often so far, or only once. So I'll invite Naomi to turn her camera back on now. We will try and get through some of the questions now. We've had 3 questions about the tilt of Uranus. And I know you mentioned that in your presentation, Athena, but I wonder if any of you could kind of just expand on why we think Uranus has got that, you know, extreme tilt compared to the other planets.
Yes, it is one of the questions we're asking actually ourselves, but it's true that several of the models today indicate that there could have been, you know, like an impact in the system that has tilted Uranus the way it is today. There are models that explain that very well, but for it to have persisted for all this time, you know, is the big question. How didn't it, you know, change that somehow it has stayed vertical as we see it today? So it is one of the questions we're going to address with a future mission. This tilt is really, like I said before, you know, something we wonder about.
Thank you. We've had a question from Facebook from the people watching over there, which is actually really good, and I don't know the answer to this question, so it's a really interesting one. I hope one of you knows the answer. Why do we always illustrate Uranus as blue? In all the textbooks it's blue, and they say, is it because there's lots of methane on the planet? Naomi, any ideas?
Yeah, so invisible, when we look at it with our eyes, it's this like beautiful, like light sky blue color compared to Neptune's like deep blue color. We're still not 100% sure why the two planets have two different blues, but we do know that that blue is the same reason that the sky appears blue when you look up. The methane in the atmosphere like reflects blue light back into your eye, and so that's why you see blue. But even with when we look at images that are from the infrared, we don't actually see it in blue in the infrared. It usually comes down to us in black and white, but artists usually make it recognizable and distinctive by coloring it into a blue color, so that we recognize that it's our famous ice giant.
Thank you. That's a very comprehensive answer. Brilliant. I hope that helped. Now we've had quite a few questions, in fact, about super ionic water, and I think most of the questions relate to what is it, and can one of you explain a little bit more about why it's important on Uranus?
Athena, do you want to? I mean, I can explain the stuff below that, I suppose, but super ionic water.
Then I'll comment if I need to, Naomi. It is a complicated answer, so I'll hand it off to the new generation.
So, like, what's happening? We don't really know what's happening underneath, like as you get deeper and deeper into Uranus and Neptune, and what we think is happening, because we know that there's probably a lot of water content. What happens when you like squeeze water in the deep pressures that you get at these planets, you end up with very strange things that that you wouldn't expect, you don't get naturally on Earth. So scientists, people in labs have squeezed water in like laboratory conditions and seen what happens. And what they found was when you squeeze it, you end up with this super ionic water, which is this basically squeezed, and it conducts.
It creates like crystal. It's a crystalline phase. Applies to all kind of ices. You can do this with all kind of ices, as Naomi's saying. It's high pressure, high temperature phases, and then you squeeze it, and oxygen ions really would occupy a crystalline kind of phase. Whereas the protons diffuse in liquid like manner, this time you have this crystal forming. It's a complicated answer. Quick kudos to Naomi.
It's very strange. It's like hot and black ice that so oxygen, hydrogen and oxygen, the oxygen like forms together into like a lattice, and then the hydrogen atoms like flow between them. So it's not a solid or a liquid, it's like this other thing. And it conducts electricity very well. So it might be why we have strange, like very high magnetic fields in both ice giants. But again, we just don't know whether this is actually something that is down there or not. And an orbiter will be able to tell us more.
That's incredible. Thank you. That has definitely answered the question, but it was complicated. But I think hopefully that, because we had questions relating to the magnetic field in relation to the superionic water as well. So that's really handy. We are really limited on time, but I am deciding to run a few minutes over because we've got a few more questions I'd really like to ask. So I'm just going to ask you very quickly about, can we look at organic molecules in the atmosphere? And also someone's asked, can we see elements such as mercury? Specifically, and that's a question from Christian.
Yeah, we have detected. I mean, we have detected acetylene, and as I recall, in Voyager data already at the time. So there is some organic. There are some organic molecules there. We don't know how evolved the degree of complexity of this organic chemistry is. This is something that, you know, as we were both saying, will take more in situ observations at deeper length, in the atmosphere to find out what is lying between the cloud layers. But we do have some organic molecules there, except that we are not looking for organic chemistry in Uranus, because that is not going to be a habitable environment. There's no surface to work on. So we're going to look for these things with the moons that I was describing before. So one of the slides I showed had this dark material that is something that could be organic material on some of the icy moons. So this is something that we're going to investigate more with James W. Or other telescopes.
Yeah, and that's often the case with a lot of these planets. Their moons are actually sometimes, you know, a more habitable environment, more similar to Earth. So brilliant. I think we're going to have to call it a day. I'm really sorry for all the questions that we didn't get through, but I hopefully combined some questions so that we actually answered more than it seemed. But yeah, thank you. If you have any further questions specifically for our speakers, then please do get in touch with them. Their emails are on the screen. We have had a little comment from Neil, who suggests that you visit if you're in the UK at any point and you go to the beautiful city of Bath, you can visit the Herschel House, where you can actually see where the original lenses and mirrors were made that he discovered Uranus with. So that sounds great. I've never done that, so thank you for that recommendation. Have either of you been there?
No, I haven't been there, but I only just got told about it recently, to be honest. I'm a terrible Uranus scientist. I didn't even know it existed. So it was only last week that I found out about it.
Well, there we go. There we go. Your next holiday can be to Bath.
Yeah.
So yeah, well, thank you so much to both our wonderful guests today. Thank you, Naomi. Thank you, Athena. They were fascinating presentations. I've just
say one thing? I just wanted to say hello to my grandfather. He's a fellow of the society and he's watching today. He's in his 90s. So hi, Granddad.
Oh my goodness, thank you very much. I'm hope that he's enjoyed. I'm sure he has found this thrilling and love seeing you on here. Well, thank you and hello. Well, yeah, thank you again. It's been fantastic, and thanks to the audience. You've been really engaged. We've had lots of brilliant questions. Now, if you've enjoyed the webinar, then please check out chemistryworld.com/webinars for future events. And while you're there, do feel free to register for a Chemistry World account, where you can sign up to our very popular reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. There will be a short exit survey after the webinar. Please do spend a couple of minutes to fill it in if you have the time. It really helps us to bring you the best webinars possible. And I'm Natalie Starkey, Chemistry World Science Media Producer, and I look forward to seeing you again in a future Chemistry World webinar.